Hi, we're Group 15, and this is our water bottle rocket experiment.
One. That's probably nice. 2, 1.
For all of our experimental launches, we made sure to be in a controlled environment with all proper safety requirements taken into account. Now, if you're a fellow water bottle rocket hobbyist as we are, you probably wonder how high your rocket goes. Altimeters like these can get pretty expensive, so we decided to come up with a formula to help you find the height of your rocket based on forces from 12.5 newtons to 25 newtons. Now, to come up with this formula, we started with two governing equations. After some manipulation, came our height formula, which height is equal to the pressure times the area of the nozzle times the time squared over 2 times the mass of the rocket. And to ensure this formula was correct, we compared to our experiment, which will be further explained by Jax.
When designing the rocket, we identified 4 main components to control. We used a decision matrix to evaluate these components. Values were assigned based on how well each part performed in a certain category. In the decision matrix shown, each component is only judged on the applicable metrics. This resulted in us choosing PLA filament based on the cost factor. PLA and ABS will perform the same in durability and quality, but we already had a full roll of PLA filament. We chose a straight edge bottle due to the quality being more reliable and the aerodynamics being more consistent than a curved edged bottle. We chose filleted edged wings to reduce the air drag force at the sharp corners, and because the curved corners would be slightly safer if an accident were to occur and the bottle hit somebody. Finally, we chose a quick release mechanism for the release type because that allows us to be 10 feet away when launching the rocket. Our first major assumption is to ignore the effects of drag caused by extra tape put on the bottle. Testing proved to be detrimental to the bottle, and extra tape was needed to keep everything in place. However, we do not believe the effects of drag will be present from this tape. We are also ignoring the effects of drag due to the altimeter. However, we did account for the weight of the altimeter and placed an equal weight on the opposite side of the rocket. We are also assuming that the thrust will be applied instantly, rather than over the course of a few milliseconds. This is so that we can have one firm number for our calculations. Our final assumption is to ignore the calibration phase of the experiment. This is because we are comparing values relative to each other, rather than trying to get a baseline zero for our experiment.
Thanks, Jax, for that decision matrix. Now, with that in mind, the experimental setup consists of a rocket filled with water and pressurized air, a compressor, and a PVC launch tube attached to a mounting frame. To meet design requirements and constraints, the setup requires a stable mounting frame, a quick release mechanism for the nozzle, and a strong adhesive to ensure minimal risks. First, the mounting frame is made of 3 wooden planks screwed together to hold the PVC launch tube in place. The small wooden block ensures the rocket is placed at 90 degrees each time, minimizing variation in launch trajectory. To secure the mounting frame to the ground, screws protrude from the surface to act as stakes. Second, a quick release mechanism is added to the nozzle to improve safety and practicality by allowing for a release and pressure from a long distance away. Third, a combination of superglue and electrical tape is used to secure fins and nose to the rocket body in order to avoid potential detachment during flight and landing. These design elements prove to minimize risk while also meeting design requirements and constraints. Before testing, all experimental materials are gathered: the water bottle rocket, a bucket of water, a measuring cup, a funnel, a compressor with a built-in pressure gauge, a calibrated digital altimeter, and the PVC launch assembly. These components are verified for consistency before each round. After unscrewing the nozzle, water is filled to the marked line on the measuring cup to ensure the same propellant volume is used in each test. This controls thrust variation due to inconsistent water mass. The nozzle is tightened to create a secure seal, helping ensure consistent pressure conditions. With the nozzle hole covered, the rocket is inverted and mounted on the PVC launch tube. The compressor is then connected to the opposite end of the tube. It is used to pressurize the rocket to a predetermined air pressure, monitored using the gauge and held constant between trials. Once the desired pressure is reached, the altimeter is activated and secured to the rocket in the same location for every flight, ensuring consistent altitude tracking. Then all team members put on their safety goggles and step at least 5 feet away from the launch site as a precaution. A designated team member pulls the quick release string mechanism to launch the rocket. This system reduces human variability. After the flight, the rocket is retrieved. The altimeter reading and flight duration is recorded. The rocket is inspected for deformation and repairs are made before the next trial. Despite these controls, uncertainties remain, including minor differences in bottle deformation over time, small misalignment in rocket placement, possible inconsistencies in wind speed, and minor human error in timing. These are accounted for in post-test analysis and discussed when evaluating the validity of the results. This procedure is designed not only to collect meaningful data on flight performance, but to confirm whether the design fulfills the project's performance and safety requirements.
For uncertainty analysis, we had to account for the uncertainty of our equipment. We had a scale, graduated cylinder, a stopwatch, and pressure. For the stopwatch, the uncertainty was due to human reaction time. On the right, we have a table that shows the average heights from the altimeter. And then we also have the table below it, which shows the calculated heights and uncertainty, which is calculated through error propagation. For our error types, we have our equipment accuracy and then also the construction wear on the rocket itself, cracks and bends from it falling back to the earth from large distances. The altimeter also had a minimum height requirement. It had to get above 0.82 meters, otherwise it wouldn't read. The environment also affected because we were out in an uncontrolled environment, so wind and rain affected the conditions of the rocket. We also used a student's T to minimize the amount of wear affecting the final uncertainty. The difference between theory and practice wasn't very large for the first three pressures. They were in very similar ranges, but as they got to higher pressures, the margins between the two, between theory and measured heights, varied greatly. For error propagation, we used the top equation to calculate our theoretical height, which was given in that bottom table of that slide shown before. But this error propagation was through derivatives of that equation and the uncertainties of the equipment to give us our errors.
Based on the flight conditions, each rocket has varying heights and times, even at the same pressure. So student T analysis was done using the 10 data points per pressure, and the average uncertainty for time was around 0.15 seconds. The student's T analysis was also done for height from launch variation, and the uncertainty was around 1 meter. This graph shows the expected height at different forces, where force is pressure times area. So bottle rocket enthusiasts can input their pressure and area and approximate the max height for forces between 13 and 26 newtons. Further testing is needed to make sure that this works for different rockets than ours. The act of making a linear fit has its own uncertainty based on the deviations between the measured points and the linear fit. And the height uncertainty for this graph is 0.89 meters. We took 20 samples at 40 psi. These heights were measured with an altimeter, which rounds to the nearest meter. The bends were also rounded to the nearest meter. Heights at 40 psi are assumed to be representative of the launch deviations at other pressures. Using a population mean of around 11 meters taken from the theoretical heights, the expected frequencies for each pressure were found using z-table probabilities around a sample mean. The biggest difference between observed and expected frequencies was at a height of 9 meters, which 9 meters heights occurred when the bottle rocket veered off course. Using chi-squared analysis, the experimental is less than the table value, so we can approximate the height deviations as Gaussian, which is how we could do the previous student T on height. We did not end up doing a calibration. If we would have calibrated with pressure, then we would have measured a known pressure with the pressure gauge multiple times to find the uncertainty with repeated measurements.
Thanks, Sage. Overall, the formula we derived compared to the data was more accurate at lower forces. To get matching results for your water bottle rocket, ensure that the forces range from a minimum of 12.5 newtons to 25 newtons. In the future, we would likely change a few things to help get more accurate results. The first thing is to do trials in a more controlled environment, like a large gym, to help neglect the effects of wind. Another thing to change is to analyze the effects of thrust force from the water to air ratio in the bottle. Both of these changes would greatly affect the accuracy of our results because these areas were where most of our assumptions were made. In the end, even with these assumptions, the formula can still be useful for average water bottle rocket hobbyists like us. Thank you for watching.